We've been studying first-order nonlinear differential equations. So generally, a first-order nonlinear differential equation can be written like this. And because that right-hand side function f could be any kind of combination of t and y, we're very limited in the analytic solution techniques we've got to deal with things like this. So if the equation is separable, we can solve just by anti-differentiation. There are many clever substitutions that we could try, but they're limited in their applicability. Same thing with an exact differential equation. If we get lucky and we can write this as a differential, an exact perfect derivative of a multivariable function, then we could get somewhere. All of this is meant to imply to you that we should probably try to develop another approach. And that's exactly what happened in the history of DEs. People tried to get these solution formulas and eventually realized that they could only go so far. So they tried to develop another approach that didn't rely on the solution formulas at all. So we're going to call this a qualitative analysis versus a quantitative formula. Quantitative means you can get quantities, you can get numbers out, formulas. Qualitative means you get the quality of this. You understand how it behaves even if you can't make numerical predictions. To try to motivate all of this, we're going to talk about some population growth models. Now, the simplest population growth model kind of looks like this, where you've got the rate of change. We'll talk about y of t being the population as a function of time. And the simplest models say, okay, y prime, the rate of change of a population is proportional to the number of individuals in the population. So this k will be positive, and we'll call this the growth rate. Now, this growth rate you could think of as the rate people come in to the population versus the rate people go out. So death, migration, that kind of thing. We already know that this is a first-order linear problem. We know that the solution is of the form e to the lambda t. So if you sub this in, you'll find that y of t has to be c e to the kt. If you have an initial condition of y naught, some initial population, what you'll find is that the solution formula is y naught e to the kt. So this is exponential growth. Now, exponential growth isn't always the most realistic. Why? Because the population grows without bound. Regardless of what your initial condition is, the entire population always grows, and the longer it goes, the faster it grows. So this isn't necessarily realistic. So what people have done is tried to modify these population models. So a modified version of this is something called the Logistic population model. And it's effectively a way that people decided to model population growth and incorporate some brakes on the whole operation. The bigger the population gets, you can imagine that it can't just grow indefinitely, right? Resources will become scarce. Space will become scarce. The more people there are, at some point the population growth has to slow down. So the logistic population model works a little differently. It's going to have, again, some growth rate factor here, but there's an additional term in front of that y. So here, we'll say that k is the growth rate, and we'll say ye is some constant. And a little bit later, you'll see what that constant has to be. But effectively, this term right here, this decreases to 0 as the population approaches this value ye. These two terms work against each other. As y gets bigger, this term wants to increase, but as y gets bigger, this term wants to decrease. So they'll eventually settle on some sort of value. Now, when you study the logistic model, we have been studying things analytically all semester long. So you could solve this by basically a separation of variables. This is a separable problem. And I'm not going to go through that right now, but the point here is that, yes, it's possible for you to come up with a formula. Now, if I give you some initial condition, what you'll find is that if you solve this by separation of variables, you will end up with a formula that looks kind of like this. Now, this is complicated. Of course, you could put it into Maple and you could try to graph it, but just studying this formula on its own, you might not get a sense of the behavior of this population. What is it doing? What does it do in the long run? That kind of thing. So the other approach we're going to take is to just say, you know what? Pretend like I can't even get the formula. Let's try to have the DE tell me everything I need to know about the solution without solving it. So this is our alternative. We are going to extract information from the differential equation without solving, because there's a lot of information that you can take. Now, this only applies, this kind of analysis, to autonomous first-order DEs. Now, these autonomous DEs can also be nonlinear, but what makes them autonomous is that you will only ever see an explicit function of the solution itself, f of y. Now, the logistic population model that I wrote up here is an autonomous model, and the same thing for the original exponential model. Okay. So which information will we extract? So what to take out? What can the equation give us? It's not so much what I want to take out. What info will the DE provide? So we're going to talk about something called an equilibrium solution. Now, an equilibrium solution, equilibrium means balance. And when you've got this equilibrium, that means there is no change in the solution. So y prime equals 0, which implies that y is a constant, which according to this definition of the autonomous DE we've got implies that this f of y is equal to 0. And so any y equals c, so a horizontal line, a constant, will be an equilibrium solution if f of y equals 0. So if we take that right-hand side and solve it equal to 0, we'll be able to get these equilibrium solutions. And this is where there is no change in the slope of the solution. Okay, so piggybacking right on that idea, we'll talk about something called isoclients. And this is values for which the solution slope is constant. And of course, solution slope being constant, we're going to basically say, look, if y prime is equal to f of y, that means any f of y equals constant is an isocline. Now, along an isocline, the solution slope has to be constant. So that means if I were to plot a picture of the solution, I take any horizontal line, and the solution curve that goes through it will have a certain slope. Anywhere along that line, that slope has to be the same. So in some way, we'll effectively get some curves that have the same slope along that line. So that dotted line is called the isocline of this differential equation. Now, piggybacking right off of that is the next point. Translations in time, in t. So if we have our differential equation and we say y1 of t solves this dE, let's talk about a second solution. That's just a shift of that first one, a shift in time. Is this going to still solve the dE? So if I take the derivative of this, that's like taking the derivative of y1 of t minus t naught. This is going to be y1 prime t minus t naught times 1. But because y1 is a solution, that means anytime I see y1 prime, it's just going to be f of y1. It doesn't really matter what's inside, but it will be f of y1 t minus t naught, which is essentially just f of y2. And what I've just shown is that y2 prime is equal to f of y2. And that means y2 solves the DE, and that means any shift solves the DE as well. So that means all solutions to this DE are shifted in time. If you have one solution, they're all going to be carbon copies of each other. And that's consistent with the isocline idea. Remember that the isocline said you have to have the same solution slope. Well, if your solution curve looks something like this, one easy way to make sure that happens is simply by shifting them all in time. They all look the same this way. So regardless of what the solution formula is, any shift will have to solve the problem. And that's really good news. We can pick up on some ideas that we had from calculus. We can talk about where the solution increases or decreases. We know that if y prime is positive, the solution has to be increasing. If the solution has y prime negative, that's equivalent to saying that the solution is decreasing. And if y prime equals 0, that's the same as saying y is a constant. Now, point of all of this is that between our equilibrium solutions, the solution curve is monotonic. So remember, equilibrium solutions happen when the right-hand side of that differential equation is 0. In between them, I can't have any other equilibrium solutions. So that means my solution is always either increasing or it's always either decreasing. So the solution is what we call monotonic. It's behaving the same way. There can't be oscillations. So in a first-order problem like that, no oscillations are possible. The DE tells you everything. We're going to store information about y prime on what's called a phase line. So we effectively just take one line. It's the one-dimensional version of the phase plane, and effectively we find all the equilibrium solutions, and we'll talk about whether things are increasing or decreasing, etc. We'll go through an example of this. And finally, we can go ahead and assemble some information about concavity. Remember that concavity is related to the second derivative. And the second derivative means you've got to differentiate the first derivative, which means you've got to differentiate this right-hand side, which by the chain rule is going to give you this, which then by the differential equation itself gives you that. So the second derivative is related to the product of f prime with f. You can find y values that make this equal to 0, and you can find or determine the regions of concavity of your solution. So that's the nice thing. There's a ton of information you can get out from an autonomous equation just from the equation. You don't have to solve the equation. All of this information is popping out, and all of this information is going to be useful in graphing a nice picture of the solution.